Okay, so let's talk about the graphs. Okay, okay. So we previously seen that the gravity is inversely proportional to the square of the separation, right? Now we have to draw the graph of how it actually looks like. Okay, so let's say that I have this graph, okay, and one, two, three, four. Okay, and let's say the distances are r, and then 2r, and then 3r, and then 4r. Okay. So these are the four distances that I have. Okay, and if you want to see how it looks like, so let's imagine this as a planet. Okay, and we are working on, okay, this is the distance r. Okay, and then if we go r in front of the planet, so this will be 2r. Okay, like till here. Okay, and then this will be 3r. Okay, 3r. Okay, and then this will be 4r. Okay, so let's see. Let's say we are doing the gravity values for the 4r for the 4r, right? Okay, come on. So if we say that the gravity on the surface of the Earth or on the surface of the planet is, let's say, g. Okay, so we are assuming that let the gravity on the surface is equal to, g naught. Okay, so which mean at a distance of r from the planet, okay, the gravity will be, okay, so the gravity will be right here at this point. Okay, this is the first point where the g naught is there, right? And the graph is basically gravity in newtons per kg divided by versus the distance in meter, right? Or the distance in term of r we are taking. Okay, now at 2r, if we work out the gravity at 2r, so we can say that um, g naught is equals to gm over r squared, right? This is for the first thing. Now for the 2r, we can say that um, g at a distance of 2r is basically gm over 2 and then r squared, right? So you can expand it. So G2 is equals to Gm over 4R, right? And you can see that this thing, the Gm and R are basically like constant, and you can replace the Gm over R square. It should be squared. So you can replace Gm over R square with G naught, okay? Press. So G2 can be written as G naught over 4. Okay. And G naught over 4 is basically 1 over 4 is basically 0.25. Okay. So if we have G naught right here, right? So the midway will be G naught by 2. Okay. And this one G naught wait, G naught by 2. Okay. And this way would be G naught by 4, right? And over here, there will be G naught 3 over 4. Okay. I'm basically distributing the graph into percentages. Okay. So let's say this is 100%, this is 75%, this is 50%, this is 25%. Okay. So this is how I just mark the axis. Okay. Now, so at 2r, the distance is G naught over 4. So let's just mark that distance. So G naught over 4 would be right here. Okay. So, yep, this is the second distance. Now the third distance is going to be, okay. The third distance is going to be G3 for the G3, right? So for G3, we can again do G3 is equals to Gm over 3r squared. Okay. And if you solve for it, so G3 is equals to Gm over 9r squared. Again, if you want to replace this Gm over r square with with G naught, so it will just be G3 G3 is equals to G naught over 9. Okay. And you can plot a point. So G naught over 9, 1 over 9, if you do 1 over 9, you will get 0.111. Okay. And this is 0.25. So if you do half a, so you will get 0.125, 0.125. So this line should be 0.125 and 0.111 should be below 0.125 right here. Okay. Now, okay. If you do the similar working, hmm, okay. If you do the similar working for the fourth value or at R4, so 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 at 4 you should do GM over 4R squared, right? And then hmm, you can then do GM over 16 R to the R squared, okay? Which can be further written as, you can replace this value by the way, okay, with the G naught. So you will get G naught is equal, sorry. G power G4 is equals to G naught over 16 over 16. Okay. So these are some of the values of the gravity. G naught over 16 is basically 0.0625. So it should be like right here, right? Like greater than the halfway. Okay. And let me just make the separation so that it'll be easy to understand. Um, okay. Yep. Fine. So if you draw the graph, so the graph will look like this. Let me just draw it. Okay, this is how the graph looks like. It is approximately correct. Ooh, approximately. Okay. So this is how the inverse square law looks like. Okay. This is how the inverse square law look like. Okay. So, and yes, this is how you have to make the graph. Okay. They'll ask you many time in the paper and they give you 4 mark on that. Okay. So you have to be very careful. You have to plot all the points and you have to find the values for all the point. Okay. You can also use a formula G1 R1 is equals to G2 R2. Okay, for outside. Okay, for outside. Okay, so if you are going outside from the planet, so you can use this formula. Okay, and this way you will find out or you'll work out what will be the value of the gravity at the different points. Okay, so yep. So this is a graph for the gravitational field at around the planet for one star for one graph. Okay, so let me just drag it down a bit. Okay, now we have to discuss the graph for the two planets. Okay, like if we have the two masses rather, so how will the graph look like? Okay, let me just child interest 31 graph of the field around the mass around the mass. Okay, now if we have two masses, so this is for one mass. Okay, if we have the two masses, then the graph will look like this. Mm, perfect. If we have um the two masses, okay, so the two masses will look like this. Let me just put the headings. Um, gravitational, sorry, gravitational field around the two masses. Okay. Okay. So this is gravitational field of one mass. Let me just come on. Gravitational field around the mass. Okay, perfect. Now, mm, okay. So if we talk about the gravitational field around the two masses, so the two masses, the two masses could be of the equal size, the two masses could be of the different magnitude, depends. Okay. So, yep, that's it. Okay. So let's say I have a mass, okay, and I have another mass, okay. Let's say they're not the same, okay, they're different, okay. So if you have the two masses, okay, and let's say this mass has a value of m1 and this has a value of m2, and the gravity at its surface is, let's say, g1, and the gravity at the other surface is g2, right? G1 and G2, okay, and they're separated by the distance of uh, d, right? Now you know that the gravitational field is a vector quantity and it is heavily depends on the direction. Okay, so if I draw the gravitational field line around the planet, so it will be inward. Okay, like this. Okay, for this field, for this mass m1, for m2 we'll have a smaller gravitational field because it is a smaller mass in size. Okay, and perfect. Okay, So you can see that the gravitational field lines opposing the each other. So let's say if I have the mass in there, okay, if I have the mass, let's say right here, or I would have some object, let's say rocket or something. So so I have this mass in between, okay? So on this mass, we'll have two gravitational field, okay, acting in the opposite direction, okay? If I just draw these two, if I just draw the masses, okay, so the gravitational field strength due to one planet would be in this direction, okay, of this model magnitude, okay, and for this planet would be at a higher magnitude, okay, G1 and G2, right? But the magnitudes differ as the point move from one point, okay? So let's say if it is like near to the first planet, the point looks like this, but if it is near to the other planet, the point would be like this, with this arrow smaller, okay, because it move away from the first planet, so its gravity will get weakened, okay, but the other's gravity will be higher, okay, and in between in between, like not in the exactly center, but in somewhere in the middle, the gravitational field strength for both of the planet will be equal and opposite, okay. So let's say in between, let's say right here, the gravitational field strength will be equal and opposite. Okay. So this is G2 and this is G1. I'm trying to make the arrows of the same size, G2 and G1. Okay. Now, so if we try to work out for the gravitational field, okay, at these like at these two to three different points, so the gravitational field is strength will increase from the surface of one planet and it decreases to the zero, and then it will increase and go in the opposite direction, okay. So if I just write down the equation, so the equation will look like um, on the mass, okay, on the on the mass, the resultant field will be given by given by this equation. G R is equals to G1 plus G2 with a negative sign, okay? One of the field is in the opposite direction, okay? So that is why, okay? Now, so the resultant gravity varies, okay? So let's say if the gravity is zero at some point, okay? Let's say if G is zero, GR is zero, sorry, okay, or at a point where GR is zero, at a point where GR is zero, you can say that G1 is equals to G2, okay? And let's say this point is right here. This point is right here where I've drawn. Okay, and the distance from this to this point is, let's say R. So let's say X. Okay. Can you guys tell me what will be the distance from this to the other point? Anybody please? Yes.
From where?
From this to this point. The total distance is D, by the way.
D minus
Very good.
wait.
Very good. Yes.
Yes.
D minus X. Perfect. Okay. So for if we try to write down the equation for one of the masses, so the gravitational field equation will be look like this. So G1 is basically GM GM1 over x, okay, is equals to gm2 over x2, okay, sorry, over d minus x, okay, and you have to square both the distances because the gravity formula contain the square in the denominator, okay. Now you can cancel the g out, okay, and you can make m1 over m2 the subject and x over d minus x. You can either also do whole square, okay. Fine. So this is how you can solve it, okay. If you want to solve it further, you can also solve it, okay. So yes, this is how it's. Hmm, can I draw the graph? Okay. So hi, this is how its derivation or its formula or masses can be related between the two objects, okay, masses and their distances, okay. And if we try, just a second, if I just make them separate to help you understand better. Okay, now it will be like more clear. Yep. And you can just increase this line. Okay, and over here
لحظة. استغرب. ليه؟
it can just be the three different points, okay, which
أدخل
we're
بقى
talking
باقي
about.
كده. بس. بس.
Okay, and yep,
لا. دي
perfect.
اسمي حاجة جاي.
Now,
فين حاجات؟ كده لسه أول. نعم.
okay, so if we draw the graph, okay, so if we draw the graph for this one, so the graph would look like this. They mainly ask you to sketch the graph, okay. So the resultant graph will be look like this, okay. For any one graph, like for any one of the planet. So for the planet one, the graph will start with a higher value, okay, with a higher gravity, and it will decrease like this, okay. The graph will be the inverse square law, and it will decrease like this, okay, and it will like, and then it will uh become constant at distance, okay. So this will be the graph for the first one, okay. Let's say I'm just drawing the g in newtons per kg, okay, and in distance in meters, or distance in, yep, meters, okay. This is for the first graph, okay. I've started the graph with like 1 2 3 4 line above, okay, and this is the separation, okay. This is the radius, okay. This is the radius, or this is the surface, you can say that, for the first planet, and this is the gravity value, okay. Nope, I should draw the dotted line, okay. So this is the gravity value, g dot, g, okay, g1, okay. For the other planet, for the other planet, the graph would look like this, okay, okay, like that, okay. So it should be in the opposite direction because the gravitational field strength is a vector quantity, and when you go from one point to another point, so the direction of the field changes, right? So that's fine, okay. And its surface will be right here, okay. So this will be the surface, okay, and there will be the G2, G2 in the opposite direction, okay? And this is the graph, this is the two graph for the individual masses, okay? But if we try to draw their resultant graph, so the resultant graph would look like this, okay? It should start like this, and it will be like that.
Yes, sir. Yeah.
Yes. Are you saying something?
No, no.
Okay.
Wait, sir. So this the green smaller mass or the
Yes, 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 small mass.
okay.
Okay. Now, so this is the resultant graph of both of the object. Okay, and this is how it should look like. Okay, the center point. This is a point where the gravitational field becomes zero, or you can see that G resultant resultant is equals to zero, right? So this is a point where the resultant gravitational field is zero, right? And over here, this was the point where the gravitational field was zero, right? And you should know that if the two masses will be equal, then this point would become in the center, okay? And the two gravity value will be exactly the same, right? But for now, this is not the case because we have the two different masses, okay? Come on, come on. It should just be like that, and this should be like this. Perfect. Is it? Yep. Yep. Good. Okay. So this is the gravitational field strength. Okay. The blue one is for the M1. Okay. And the green one is for M2. And the purple one is the resultant graph of both of the field in between the path. Okay. And yep. So they mainly ask you to draw or to sketch the graph. Okay. Is that clear, guys? Yes. Any problem?
Yeah.
Okay.
Yeah,
I
no.
have one question that contain the similar type of concept, and it is quite difficult in the Passover. So I just try to solve this, and then we'll move on. Okay, so this is a question. Okay. In the last part, they're asking you to draw the graph. Okay, and which is what we done in in the notes. But let's try these three parts. Okay. Okay, this is also done. Okay, so they're asking you to draw the gravitational field strength. They're asking you to define it. Okay, so once you define that, so and after that you have to make the points. Okay, and it will look like this. So the similar thing that we've done in the Vassiver. Okay, and this graph is like asked various time. Okay, after this one as well. Okay, so let's try this question. Okay, this part. We just need to take out these parts, okay? Copy. And what's here it is 2010 November 41. Okay. Now let's try this. Paste. Perfect. Yep. Good. Okay. So it is November. It is a question from um November 2010. Okay. Variant 41. Okay. Question 8. Okay. Or question 2, part C. Question 1, part C. Okay. Now let's read. So they're saying the Earth and the Moon may be considered to be the spheres that are isolated in the space, okay, with their masses concentrated at their center, okay. So these are the assumptions that they made, okay, in order for you to use the gravitational field equation, okay. Otherwise, you can't use that equation. You have to use the differential and integral form of the form of that equation, okay. Now, they've given you the mass of the moon and the mass of the earth, and they mentioned that the radius of the earth is RE, and the separation between the center of the earth and the center of the moon is 60 RE, as illustrated in the figure 1.2. Now, Explain why there's a point between the gravity between the Earth and the Moon at which the gravitational field strength is zero, right? We know that gravitational field is a vector quantity, right? And at every point, the gravitational field is basically the resultant value of the two field, okay? And since they are in the opposite direction, so that's why they'll cancel out, okay? So we'll write
Sir, can we write that it's in
mm,
equilibrium
No, no,
or
no, we can't write that. You can say that it is in equilibrium at that point, but it's not a good way of writing that. Okay, like you have to explain. They're asking, like they're assuming you to explain the directions of the gravitational field strength. Okay, and then you have to make the conclusion. Okay, so you can say that um, gravitational force is attractive in nature. In nature, this is the first thing. Okay, and and the resultant gravitational field is the the difference between the two individual field at a point. Okay. So, and you know that whenever you are finding the difference and one quantity is increasing and the other is decreasing, so you will get a point where the resultant becomes zero. Okay. So, uh, the resultant will get to zero at any point. Okay. Now, here comes the important thing. So now they're saying determine the distance in term of RE from the center of the Earth at which the gravitational field distance is zero, right? We you should know that the gravitational field far from the Earth should get zero, right? So let's say right here, let's assume that at this point the resultant gravity is zero, right? Because the Earth is very large mass, okay? So the gravitational field effect will be greater, and it will be at a very far till the very far distance, or it will be last for a very far distance, okay? So and the moon is smaller in mass, okay? So its a gravitational effect will be till the small distance, okay? So that's why the gravitational field strength of the Earth get cancelled out at a very far point from itself. Okay. So let's say this is the point, and I'm assuming this as okay. I'm assuming this distance as wait. I'm assuming this distance as x. Okay. And they're saying determine the distance in terms of RE from the center of the Earth at which the gravitational field is zero. Okay, so this x is what they're asking for. Okay, okay, and then this point will be. Can you tell me the distance for this point, please?
D minus X.
D minus. Okay,
Six-
yes,
60 RE minus X.
very good. 60 RE minus x minus x. Okay, perfect. Now, so we know that at this point, the gravity G1 should be equal to G2, okay, at that point, okay. And we can say that m gm1 over the distance 1, which is x squared, should be equal to gm2 over x over 60 re minus x whole squared, okay. And then okay, This is done. Now, the G and the G get cancelled out. Okay, so M1 over M2 is equals to x squared divided by 60RE minus x ka whole square. Okay. Now, if you put in the values of G1 and G2, so G1 is basically 60, M1 is basically 6 exponent 24, and M2 is 7.4. Okay. So 6 exponent 24 divided by 7.2 exponent 24, 22, sorry. It is 7.24. Yes, 7.4, sorry. 7.4. Okay, is equals to x over 60 RE minus x, okay, and I'm root this whole thing out, okay, to cancel the root from the other, to cancel the square from the other side, okay. So just do it, please. Yes, what's the value? It should be 3 or something.
9.128.
1 point
9.128.
9.128. After rooting it,
Yeah,
shouldn't be okay, fine.
because before routing it, I'm getting 83 point
Okay.
something.
But it should be 9.00. I remember that value. Can you please check it once again?
Okay.
Sir, it's 9.07.
9 point? Is it correct, right?
9.007.
Okay, okay, perfect. So, okay. So we are getting 9.0, and this is equal to, wait, it's just,
Yeah,
uh,
9.0. I
okay,
put 7.2, I think that's why, not
okay,
7.4.
okay, okay. So 9.0 x over 60 RE minus x, okay. So if we just solve it, so it will be 60 into 9. So 60 into 9. So 540 RE minus 9x is equals to x. When you take the x to the other side, so it will become 10x. Okay. 540 RE. Okay. Then 0 and 0 goes off. So you're getting 54 RE as a distance. Okay. Clear? Okay.
Yeah.
Okay. So now, okay. Just give me a second, please. Okay. So this concept is basically the gravitational field around the two masses. Okay, we did the graph and all of this stuff. Okay, now let's talk about the concept of the density of the planet, okay, and the density and the gravity relationship, okay. So the density, oops, the density and the gravity relationship, density and gravity relationship. Okay. Now, so if I have, let's say if I have the planet, okay, if let's say this is a planet, okay, and this is the separation, or this is the radius of the planet R, okay, and the gravity at the surface is G, let's say the G, okay, and if we try to relate the density and the gravity together, so let's try doing that, okay. So the gravity is, okay, so let's say that we have the gravity relationship is G is equals to Gm over R squared, okay, and in place of m, I can replace the m with density is equals to mass over volume. Density equals mass over volume. Okay, this is what we know. Okay, and we also know that the volume is so we are considering the Earth as a sphere. Okay, perfect sphere. Okay, so the mass is a perfect sphere. Sphere. So if the mass is a perfect sphere, so can you tell me the volume, please?
4/3 pi r cube.
Very good. 4 over 3 pi r cube. Okay. Now, if I so G is equals to, and R remains the same, R squared, and G in you can replace M with density times the volume, which is 4 over 3 pi n r cube, right? Now this r cube and r squared get cancelled out. Okay, 3. Okay, let me just make rho the subject. Okay, so rho times 3, g times 3 over, okay, over 4 pi and r and capital G is equals to rho, right? Is that clear? Perfect. Okay, so now, okay, so this is what the relation of the gravity and the density is. Okay. Acha. Now, let me just make the separations. Okay. So if we try to find out the gravity of the Earth using this formula, okay, and let's say the density, the mass of the Earth is, let's say, given to you as for the Earth, for the Earth, okay, the mass is equal to, 6.00 exponent 24 kgs. Okay. And the radius is going to be 6.40 exponent 6 meters. Okay. This is for the for the Earth. Okay. So can you find out the density of the Earth? You just need to put in the formula and you have to solve. Yes. So 3, you know that the gravity at the surface of the Earth is 9.81, okay, divided by 4 pi, and then r is going to be the r is going to be the radius, which is 6.4 exponent 6, okay, and mass is going to be 6.00 exponent 24, okay, and you can work out that, okay, come on. Yes, what's the value you're getting? Yes, any value? It should be somewhere
Uh,
around. Yes.
6.09 into 10 to the power negative 32.
What? Wait.
Yeah, I have to check again, nothing
I
else.
just put in the incorrect value. The G value is 6.67, exponent negative 11. Okay. Just correct it, please. It should be 55805504 or something.
Yeah, 5486.237.
5486. Okay. So you can either say that as 5500 rho, okay, in kg per meter cube, okay, and we consider the density as uniform, okay, throughout the Earth, right? So this is something that we assume, okay. Now, if okay, so if we somehow know the density or the composition of the Earth, okay, let's say more of the Earth's surface is basically actually in reality the Earth is made up of 70% of the water and like 25% of the rock and the land and all of this stuff, right? But and its gravity is this value, right? So if somebody gave you the gravity value lesser than that or greater than that, okay, so you should be able to predict the composition of that planet, okay. So let's say if a planet is having the density of 800, okay, 8000, okay, so its composition should be rocky, okay, more land, more surface than the water, okay, and it could be at a very high pressure, okay, because a high pressure also increase the density, okay, clear? Yes,
Yeah,
getting perfect. The second possibility is if they give you that lower density. So lower density means if like the planet or the mass would be made up of mainly water or mainly gas at high pressure, okay, or water at low pressure. Okay, so that makes the density lower. Okay, clear?
yeah,
Fine. So this is the relationship of the water. This is the relationship of the density. Okay. Now, They sometimes give you the relationship, the density relationship question in the exam, and they ask you to compare the value. Okay. Now, I have another thing, but I think let's just stop this class right here. Okay. So the next thing will going to be I'll take 1 more week for this part to be complete. Okay. This is like the biggest part. Okay. And I required a bit longer time for that. In the next week we'll complete the half of the chapter, and then we'll be left with the gravitational potential. And once done, and then the next chapter will be smaller. Okay. So this gravitational field will take a bit time. Okay, the magnetic field may take a small time. Okay, but the rest of the fields are smaller. Okay, clear. So I am keeping the class till there, for the till this point. Okay, and in the next class we'll study the weightlessness, and we'll study the the concept of the circular motion or planetary motion. Okay, so yep, that's it. Okay, Shani.
Sir,
Yes.
is this like
Uh-huh.
yeah